All right, welcome back, everyone. Welcome back to undergraduate seminar. I'm super duper glad to have you all here. My friend Sarah Brewer is going to tell us about constructing rosettes in GeoGebra. Sarah, take it away.
All right. Hey, everybody. Share my slides. So like Parker said, my name is Sarah Brewer. I'm an artist and a mathematician, and sort of for the past year and a half or so, most of my artistic and mathematical research has involved a study of traditional Islamic star rosette patterns, mostly in relation to circle packing and K-uniform tiling. So I'm going to go through a version, so slightly modified version of a talk that I gave at the Bridges conference back in August. Slightly expanded because I only had like 10 minutes at that talk. And then I'm going to walk through some of the construction of some of these things. So let's kind of start by unpacking some of that terminology that I just kind of threw out there. Let's see. And I'm going to start by talking about Islamic star rosette patterns. So most, I would say, this sort of general term of Islamic geometry or Islamic geometric design, most people kind of have in mind things like Moroccan tilings. That sort of is the picture that's brought to mind. But basically, that term refers to any of these geometric patterns from any of these parts of the world that were once under caliphate rule. So anything from India to Spain, Northern Africa, Middle East, etc. And I'm not going to be talking about all Islamic geometric patterns, although certainly I do practice those artistically. I'm going to be focusing on what are referred to as specifically star rosette patterns. So I'll just kind of go through, I'm going to show you a few examples as I kind of explain what these things are. Hopefully between the last slide and this one, maybe you've already started to get an idea. So basically, these patterns are characterized by these rings of hexagons that are sort of petal shaped, right? And they surround a star polygon in these sort of flower-like rosette formations. And in between these flower-like rosette formations, you see often 5, sometimes 6 or 7 pointed stars or partial stars. And these patterns can be very, very simple. So they could just be stars and petals with very few numbers of sides and points that repeat in a very, very simple pattern. Kind of the one in the middle here is one of the simplest. Or they could be very complex, and you can have star rosettes with different numbers of petals all mixed together in the same larger construction. So it's generally agreed upon in the Islamic geometric design community that these patterns follow specific rules. So some of those rules, I'm not going to go into all of them, but essentially, biggest rules are that at a crossing, lines should not change direction. Okay, so that's a big one. And your petals that are making up these star rosettes should have certain proportions. And the outer 4 edges of those petals, so the ones that are making up sides of the adjacent stars, we want those to all have the same length. There's more rules, but those two kind of get us most of what we need. So it turns out that these particular patterns are so mathematically elegant and simple that you really don't have to work very hard or think very hard at all in order to actually achieve those ideal proportions, as long as you understand the underlying structure. Now, a bit of an aside, um, I started studying just Islamic geometric patterns in general, probably around 2010 or so, and I was mostly using them as examples of wallpaper patterns. So I taught this elective class called Visual Mathematics, and one of the little units that we would do was just about the wallpaper groups and identifying symmetries, and we would make tessellations and all this kind of fun stuff. And because of some of the weaving that you see in Islamic geometric patterns, and because there are so many different symmetries, they were really great examples to pull from. And what's ironic is at the same time, I was also teaching compass and straight edge construction of just things like regular polygons or, like basic Euclidean stuff, like how do we inscribe a circle or circumscribe a circle. But I wasn't combining the two at all until around probably 2017 is when I was like, well, duh, I obviously need to learn how to construct these things because I'm already doing compass and straight edge constructions and I'm already studying these Islamic geometric patterns. So it totally made sense to combine the two. And there's a ton of tutorials and books out there now. There weren't that many resources just 5 years ago. But thanks to the pandemic, like, man, there's so much stuff out there now. But I would say sort of the biggest game changer for me was this video that my friend Samira Mia put out where she was comparing two different approaches to drawing what people refer to as the ideal or the canonical eightfold rosette. And depending on whether you're following a sort of traditional approach to constructing these patterns, or if you're following, let's say, a not so precise, quick and dirty kind of approach that a number of people were using 5 years ago, you get different results and you don't get those nicely proportioned petals that we agree in the community you want to see. And when I was constructing the canonical version, I quickly began to like see, ooh, there's this really lovely circle packing going on in this pattern. Like if I go back and, we look at these patterns in tile work or wooden inlay, you don't see any of that underlying construction that goes into making these patterns, right? You just see this sort of final pattern. But when you're actually constructing them by hand, you're seeing all of these lines and circles that go into them. And so I was like, okay, circles, gotta just sort of deep dive into this. And that led into like just I had a student research group studying circle packing and Islamic geometric patterns in general. And then I guess about a year and a half ago or so, I had a student research group that worked with me to write the paper that I eventually presented at Bridges. So sort of the progression from constructing this canonical eightfold rosette to, weird GeoGebra explorations like you see on the right, took sort of a detour through the work of Anthony Lee that was introduced to me by Daoud Sutton at the first Princess School of Traditional Arts Geometry Summer School in 2018 in Scotland that I was very lucky to get to go to and nerd out with all of my Islamic geometry pals. But basically, like Anthony Lee kind of lays out the mathematical foundations of these patterns. And, these are just a couple of pages from his journal that have a lot of pictures, but he certainly, goes into which patterns are topologically equivalent and all sorts of fun things. Everything is in his very specific cursive handwriting. And so reading hundreds of pages of this is pretty tough. Thankfully, my friend Alan Adams, who's a retired chemist who studies Islamic geometry, hooked me up with some nice transcribed versions and also a couple of summaries that I was able to give to my students whenever they were helping me out with this stuff. But anyway, so that's kind of where we are. So how do we get to these like K-uniform tilings and circles and all this other stuff? So essentially these patterns, so you've got a partial 12 and 8 star rosette on the left and a kind of more fleshed out 12 and 9 star rosette on the right here. Obviously, we're counting petals, right? So there's 12 blue petals around and 9 yellow petals around on the right. So that's why I would refer to that as like a 12 and 9. But it's not just about the numbers of petals, it's about the angles of those petals. And traditionally, those rosettes are only going to have very specific angles that are tied to star polygons that have the same number of vertices as the petals or double the number of vertices of the petals. So in case we don't know what a star polygon is, so in general, an NK star polygon, you're taking n vertices arranged in a circle and you're connecting a vertex to the next vertex that's k away from it. So if you have an N1 star polygon, it's not really a star, but it's just a polygon, right? If you have an N/2 star polygon, so you're connecting a vertex to the one exactly opposite it, assuming n is even, then you just get an asterisk. Otherwise, you get some kind of a star shape, right? So if I'm connecting 5 vertices with the sort of pentagram style star that most of us have drawn since we were kids, that's going to be a 5/2 star polygon. Okay. Now, things can get a little bit interesting when you start talking about whether n and k are relatively prime to each other. So if k is relatively prime to n, then you're going to visit every vertex without picking your pencil up. If k is a factor of n, or they share a common factor, then you're going to form a polygon or a star polygon that's a subset of the number of vertices that you start with. So for example, this 12-3 star polygon up here, you can see that it's a composite of 3 squares. So it's this idea that lives in the middle of these star rosette patterns. So on the left, and I'll pull up the actual GeoGebra file for this a little bit later, but on the left, you can see points P and Q here. So you've got a 17, so here N is not exactly the N in the last slide, but here N is how many petals do I want my rosette to have. And traditionally, right, you're either going to be dealing with a star polygon inside that rosette that's based on exactly n points or 2n. So here I've got a 17-fold rosette, and I've made 34 divisions of my circle. So 34 equal divisions, so 34 vertices. And I'm connecting point P, in this case, to point Q that's 10 vertices away. So I have this 3410 star partial star polygon in purple here, right? You'll notice I'm omitting every other vertex, right? So this is really equivalent to a 17.5 star polygon. The reason that I have it as a 3410 rather than as a 17.5 is so that I could adjust Q to one of those in between vertices a little bit more easily if I wanted to. So say I wanted like a 34.9 or a 34.11. I don't have to mess with my GeoGebra code too much. Now, whenever I was like teaching my students how to do this stuff, this is kind of the paradigm that we were working in because that's traditional construction, right? And when you're dealing with a traditional art form, the community is like, okay, you have to follow the rules, and you know, we want everything to be perfect. Well, I was following the rules and, you know, constructing things as exactly as they should be. But I was still getting patterns that didn't exist in nature, or, you know, in nature, out in the wild, as we say, right? So thankfully, one of my peer reviewers for the Bridges conference was like, why are you doing this star polygon thing? Like, it doesn't make any sense. Why not just have a variable angle? And I was like, you know what? You're right. I don't know why I'm still doing that. So most of my GeoGebra now is just based on an angle.
I'm going to jump in because you said it a couple times. Bridges is an awesome conference about math and art. It's not well-known outside the math art community, but Bridges, we should all read papers and go there. It's awesome.
Yeah, so it's the international conference that occurs every year. I could never afford to go there until they started doing it online. And so I presented online this year, but they're probably going to go back to in person. I hope I can afford to travel to go there because it's in all kinds of cool places all over the world. Maybe your department will give you some funding if you write and present a paper.
Yeah, let's do it. Let's make it happen. Sorry, just for context.
Yeah, no, for sure. When I discovered the Bridges conference, I was just like, ooh, these are my people. So but anyway, yeah, so this star polygon is defining the angle of the rosette. So that's sort of the main point there. Let's see. Okay, so traditionally, right, these patterns are constructed with a compass and straightedge, and like this is what we see in the final pattern, right? This is the tiling we see, or the stone jolly screen, or whatever. But these are constructed with circles and lines, right? They're built on this grid. And depending on, say, the number of petals and the symmetry of the pattern, sometimes the circles overlap, sometimes they don't. You know, depending on what sort of circle packing paradigm you're working in. You know, sometimes you want that univalent circle packing. So that's what we see on the right. Your circles are perfectly tangent, they don't overlap. But in some paradigms, it's perfectly fine for your circles to overlap, and you can do all kinds of neat, weird circle packing things. I went to this amazing Brown University ICERM workshop a couple of years ago on circle packing and geometric rigidity. It's amazing. Some of those lectures are online, by the way. But anyway, so here are two sort of very classic patterns, 10-fold rosette on the left and 12-fold on the right. And if I sort of strip away the pattern, right, all we're left with are those circles. So there's your really nice univalent 12-fold packing, and that, because of simplicity, that's sort of what we ended up focusing on. And when I say we, I mean myself and a couple of students that co-authored my Bridges paper with me. Mostly because this was sort of an easily teachable method, and even just sticking with the univalent circle packing, there's almost infinitely many geometric patterns that you can construct from these things. So we've got this circle packing where our circles are nice and tangent and don't overlap. If we connect the circle centers to each other, we get what's called the intersection graph. So you can do all kinds of fun graph theory studies of these things, but I'm not going to get into that. But that intersection graph for all of the patterns that we're going to look at qualifies as a K-uniform tiling. So that's just sort of a more general term. That means in your tiling, you have K different vertex types. So, you know, a vertex type being like, okay, at this vertex, I have 3 hexagons together. At this vertex, I've got 2 octagons in a square, but not just different polygons at that vertex, but they're independent in that, like, sort of their how their adjacent polygons are also, because you may have like 2 different vertices that have the same arrangement of polygons around them, but because of in between stuff, they count as different. Anyway, so when I was having my students learn how to construct these patterns, I basically just sent them to the Wikipedia page on K-uniform tilings and was like, hey, pick your favorite tiling. Let's build a pattern on it. So I like patterns with dodecagons. This has a dodecagon and a nice little collection of tilings there. So let me kind of show you step by step the way we went through this process. So we pick our favorite tiling. We construct it in GeoGebra, and basically I don't need the whole pattern. I really only need the minimal triangle. So what's the smallest part of that whole pattern that I could repeat through reflections and rotations to generate the entire thing? So here For this particular pattern, my minimal triangle is the center of a dodecagon, the center of the hexagon, and where the two dodecagons meet. So that right triangle is what I want to focus on. And then I can easily generate the rest of my pattern from that. So we've got this K-uniform tiling. What we want to do from here is find the midpoints of all the edges, and we're going to construct circles whose centers are the vertices of that intersection graph, and their radii are drawn to the midpoints. So these K-uniform tilings, I should note, one of their defining characteristics, right, is that they all have equal edge length. So it makes constructing a circle packing on it real. That's one of the reasons why it's so easy to construct a circle packing on it. So all of these circles that I've constructed here have a radius that's half the edge length. Now, we were sort of trying to follow kind of this circle packing paradigm laid out by Kenneth Stevenson and some of his co-authors, where, you know, for a univalent circle packing, you want kind of this group of 3 tangent circles always. You don't want 4 with this like curvy square space in the middle. You don't want 6 around. You certainly don't want 12 around. So to fill those gaps, we draw in a few more lines, right? So I connect, you know, the centers of my circles, and I fill in circles in the square, the hexagon. Basically, anything that's not a triangle is going to need an extra circle filled in. And in terms of getting like classical Islamic geometric patterns, I would say the little circle inside the square is often omitted. If you do that, you end up with octagons, but we're going to end up with like a 4-pointed star there instead. All right, so this is kind of the next key bit. So we've got all of our circle centers connected. We've got these, what I refer to as radii of tangency, so line segments that go through the points of tangency between circles. The next thing we want is between any 2 radii of tangency, we want to find the angle bisectors. So I'm just going through and finding all of the angle bisectors. Again, just inside that minimal triangle, I don't need to worry about any of this stuff outside the minimal triangle. So for simple patterns, you know, it's not too bad. In more complicated patterns, you end up with a lot of lines drawn in GeoGebra, and you've got to be careful because a lot of things on one side might be an angle bisector and they kind of look like an angle bisector on the opposite side, but they're not actually. So just kind of warning there. All right, so then comes our generating line. So you can imagine this dodecagon at the top right. In my earlier paradigm, I would have rotated point P some number of times to get a collection of vertices, and that would be like a star polygon line. So I would connect point P to some other vertex. And that's what you would do if this were a pattern in the wild, right? I would connect point P either to the point of tangency to another one of those circles or the in-between points. But we're fancy with our fancy software, so we just make a little slider that lets us change the angle. And then once we have this line that's at some angle to that radius of tangency, and notice I positioned it on my dodecagon You really can position this line at any of the points of tangency between two circles. I just sort of tend to, sorry, my cat's about to walk across my keyboard. I tend to attach it to my largest circle, just because. And then once we've got that line, all we have to do is just reflect that line over every single radius of tangency and every single angle bisector. Wow, that was easy. So basically, you find like where these things intersect, and hopefully kind of if you isolate one little part, you can see how the edges of all these little polygons that I've got in here, they share a mirror image over one of those radii of tangency or the angle bisectors. But what's really cool is that like if you have your circle packing and you have this line and you have those, all this sort of underlying structure, reflections get the job done. And I really like this sort of idea that you can generate the entire pattern with reflections. I really owe like a huge debt to my friend Ricardo Hinojosa, who's an origami artist from Monterrey, Mexico, who folds Islamic geometric patterns with origami. And probably like the first year of the pandemic, I spent ungodly hours with him on Zoom, just folding these patterns, and it was amazing, and a lot of fun. And Parker brought us on to give a talk at Gear
So
about
just
that.
a shout out. Part of the context here is Professor Shabazi and I organized a conference called GEAR, which is Geometry, Education, Art, and Research. And Sarah and Ricardo were speakers there, and I learned so much geometry during that thing. Also, weirdly, I don't know if I've got some gossip, so I'll share it later. There's gossip about gear. It's coming back, but
Awesome.
that's not relevant to this talk.
All right, so then kind of once you have your minimal triangle, right, then you reflect and rotate and generate the pattern however much you want. And I'll pull up a bunch of examples and you can kind of see how these guys work. It's obviously a lot cooler when you can see the angles change too. One of the things that really kind of stood out to me as I was constructing these was like, as you're playing with the sliders, going from like no angle to a 90-degree angle, is that those star polygon lines forming the actual Islamic geometric pattern that you would see out in the wild, they're really forming this sort of family of transitions from your original K-uniform tiling to its dual tiling. And that's something that, I really want to explore further. Just I haven't yet. I'm getting there. I was hoping to have more on that by now, but life sort of gets in the way, I guess. But I'll pull up this pattern also. So I sent Parker the links to my GeoGebra page and my bridges paper that he's going to share on the seminar page for you guys. And you'll also get my slides that have links to some pretty cool papers and like historical documents with cool patterns and some books and all that sort of stuff. But without further ado, let's pull up some GeoGebra. So I always use GeoGebra Classic 5 rather than GeoGebra 6 because I don't like how GeoGebra 6 tries to auto format my inputs. So if you're a GeoGebra user, or if you're not a GeoGebra user and you're looking to get into it, that's something to kind of keep in mind. You know, maybe it's because I grew up using a TI-89 and didn't have like pretty math print and had to mind my parentheses and things, but anyway, just the input. So let's see. Sure, we could start with this one. I don't know if the order really matters here, but I just kind of picked out a few of these to share with you all. So here we've got a 2 uniform tiling, and we can watch as the slider moves. And one thing I neglected to mention, so we've got yellow petals and blue petals here. And there's always a unique angle. So here it's 30 degrees that gives you parallel-sided rosettes. And that's often sort of a goal with these patterns, is everybody likes parallel-sided rosettes. But notice I can't, for this particular pattern, I can't have parallel yellow and parallel blue. If I wanted to have both parallel yellow and blue, I'd have to change some other rule. So I'd have to compromise. We refer to petals where the outer 2 edges of the petal converge as you move outward from the rosette as convergent petals, and petals that diverge, so the sides here, as you move outward as divergent petals. You see different types more or less often in different parts of the world. So that's just kind of little thing there. But like, look, woo, pattern too. Well, some of them you get weird overlaps, but you imagine the overlap's not there and you get pattern to its dual. So that one's fun. I'm just gonna kind of pull up some of these. One of them broke my computer earlier. Hopefully that won't happen again. Let's see. So this guy's 4 uniform tiling. And all of the ones that I'm showing you, I have public on my GeoGebra page, so you can download them and play with them and edit them and break them. You know, whatever, to your heart's content. They're fun. Let me find, let's see. So I got about what, 5 more minutes and then we take questions, or?
Sure. Yep. A, that was awesome. That was a lot of cool stuff. B, the format is totally up to you. So when you want to start taking questions, I'll put the feedback form, which is very important because that gives us our snacks.
Okay.
So we do feedback form and then questions after.
Okay. Well, I mean, you know, for now I'm just sort of showing some examples. Love the animation in GeoGebra. So I have these set up to increment every 0.5 degrees, but you can choose what you want that to increment in GeoGebra. In theory, most of these will take on any real numbered angle from 0 to pi over 2. I always stop at 90 or pi over 2 just because you get repetition. If you go beyond that, you end up with the same patterns again. So this one's fun. I'm trying to think of what would be a good one to kind of click through the construction protocol of. I don't think I showed this one. Oops. see. So I'll show the slider at first. Can you tell I like rainbows? All right, so what we're gonna do is I'm gonna make sure I'm showing all the things, and it's gonna really bog down my computer.
Oh.
Let's see. Oh, it's already. Oh, come on, you can do it. It's those points that really does it. Okay, so maybe that's all the things. We'll see. And I'm going to pull up the construction protocol. So this is kind of a cool thing that you can do in GeoGebra if you have something that you want to learn how to recreate. As long as everything is visible, so this is 229 steps, I can click all the way back to the beginning. And I wonder if I just click play, how fast this will. Oh, I guess ooh, maybe I should pause it. Yeah, so I don't have everything on the screen. Let me zoom out a little bit. All right, there we go. So I'm starting with points. I didn't call that point A4 originally. I probably called it A and B. So this is me, right, constructing that K uniform tiling. Actually, I think I'm just going to click through it because it's kind of slow. So I'm constructing, I'm making like perpendicular bisectors and various line segments and things to find some of those midpoints. And so this is me just constructing line segments between polygon centers and where I know there are going to be circle centers and starting to fill in some of those circles. This pattern, because it has a rotation in it, I constructed a little bit more than just a minimal triangle. Just because, yeah, I don't know. It's nice to see, right? But so you can see like this stuff gets like really messy with all the lines and things. So I'm constantly like hiding stuff, cleaning stuff up as I go, usually hiding labels all the time because those things are gross. But anyway, and so you eventually kind of get there. Now if I go back and hide some lines and hide some points, it's mostly yeah, and so like my you notice I'm hiding all of my polygons. So I tend to generate like sequences of polygons. And then I generate sequences of polygons just because my computer likes them a lot better than if I try to draw like 100 polygons. So yeah, so absolutely like grab my GeoGebra files, download them, play with them. I have a few tutorials up on YouTube. Yeah. I guess that's about it. I'm more than happy to answer any questions, show more examples, whatever you guys want.
Sweet. So at this point, I'm going to put the feedback form in the chat for the people who are online. I'm also going to hand around the all-important snack sign up. If you could fill this out. So we'll take let's say 3 minutes to fill that out, and then we'll get into questions.
Awesome.
Um,
I'll turn an animation on in the meantime.
So, yeah, these are super duper duper cool. Thank you for sharing this stuff with us.
You're welcome. It's fun.
So people in the chat, please fill out the thing. It's very, very handy.
You don't need me to fill it out, right?
It also is a mechanism that we use to give feedback to our speaker, to say what people liked about the talk, what could be improved. Well,
Let's see. Oh, here's that discrete star polygon that I kind of mentioned earlier in my talk. So you can choose how many petals you want and then play with the angle. So that one's fun. Whee!
Snacks, I know, super important. Oh, here, I've got a pencil.
And then here's continuously varied.
Oh yeah, so the gossip is that year is going to happen again. We're currently negotiating with Beth to see if we can get it in person. But we'll definitely have an online component so that you and Ricardo can come show us your awesome stuff.
Cool. Let's see. Oh, this is the one I
Ricardo
broke.
does this stuff, but out of paper folding. So like one of the cool things about paper folding is reflections are free in paper folding. You just fold the piece of paper over the line and that does the reflection for you.
Yeah, and like stuff like constructing angle bisectors and perpendicular bisectors and all these like compass and straight edge constructions that take like 5, 10, however many steps, like you can just do in one step in origami, and it's so nice.
Yeah, so there's this kind of cool math thing that origami is somehow like more powerful than reading compass. Like it can just, yeah, you can do these things as Sarah was saying, take 5 steps, just like fold the paper. And then it's
You
done.
can trisect angles.
Yeah, you can't draw circles, right? So that is one of the things that is much harder in origami, drawing circles.
This is true. This is true. Circles are one thing that compass has that origami doesn't.
Sweet. Okay, there's our 3 minutes. Are there things people want to ask? Are there things in the chat people want to ask about?
What did you mean by like it approaches its dual? Like what is a dual in the context of this?
Yeah, so let me pull up.
What is a dual in this context? Yeah, she
Dual,
mentioned.
yeah. So let me pull up this pattern. So oops. Come back. Let me see. Okay, so can you see my original tiling here that's just the squares and the triangles, and then I've got a dodecagon here? Okay,
Yeah.
so that tiling has vertices at the vertices of the squares, triangles, and dodecagons, right? So the dual of that tiling swaps centers of polygons and vertices. So the center of each of the polygons becomes a vertex in the dual tiling, and the vertex of a polygon becomes the center of the polygon. So if we sort of watch the pattern here, so aside from like some inserted triangles and things that weren't part of like they're the sort of the modified K uniform tiling, I guess we'd say. The lines are exactly on the original squares and triangles and dodecagon, right? But as we move to 90 degrees, my vertices move away from the vertices of the original tiling and toward the centers of those polygons. And so you get not a you get the dual tiling that has like different edge lengths and you know has different properties, but they're obviously you know very much related, and you end up with the same symmetries and that sort of thing. Good question. I see a question in the chat. What are the best resources to learn how to use GeoGebra? Honestly, number one, like have a goal in mind of what you want to do in GeoGebra and just play and like, because there's so much that you can do in GeoGebra. Like it's going to be like your specific thing that you want to do. Like most of the time, I would say, especially like if you're, I don't know, a weird math art person like me, most of the time there's not a tutorial of how to do the thing that you want to do, right? So it's a question of like, okay, well, what tools in GeoGebra will help me achieve what I'm trying to do? And whenever I kind of first got started in GeoGebra, my constructions were super clunky, and like I didn't know how to use sliders. I didn't know like how to make sequences of polygons and all these kind of nice things that GeoGebra really kind of lends itself to, right? I was really treating it like I was doing a compass and straight edge construction just on my computer, which is certainly fine, right? And a lot of my friends in the Islamic geometric design community will approach GeoGebra like that, because it's kind of a good way to analyze patterns and check to see if your compass and straight edge construction of a pattern that you found is actually correct and that sort of thing. You know, but I ended up like, I learned a lot of stuff just sort of here and there from different folks. I learned a lot of GeoGebra from John Bowers when I was like studying rigid origami. I learned some GeoGebra from somebody that was showing how to do like origami crease patterns at the Origami USA convention. I don't know, like I've tried to kind of follow GeoGebra tutorials, but most of the time they're not anything that are what I'm trying to do in GeoGebra. So there certainly is a huge knowledge database out there of how to use GeoGebra, but again, just sort of depending on what you want to do. Really just play and ask people.
So it's now the top of the hour. Let's thank our speaker. That was fantastic.
Thanks so much for coming and having me.
Next up, next week, we have a local. We've got Alex Teeter, who's going to tell us about the classification of surfaces. I know he's super duper stoked. Last year he gave a talk on knots, I think. Yeah. So yeah. Next week, what is that? What are muffins? We have extra muffins. Please take some on your way out. Thank you again, Sarah. That was wonderful.
Yeah, thanks so much.